Okay, good morning, everyone. Okay, so we're going to start our lecture now. All right, so today we're going to start a new section, and in fact, the final section of the course, which is about approximation algorithms. Okay, so we'll try to talk about these problems I'm listing over here. We'll see how far we get. Okay, so first of all, to introduce approximation algorithms, so I talked about this last time, and basically the idea is that we have lots of optimization problems, and many of them are NP-hard. Okay, but because they occur quite often in practice, we still need some way to deal with these problems. And there are different approaches to doing this. For example, previously we talked about, well, maybe if you have a difficult problem, you can consider special cases of this difficult problem, and that might make it easier to solve. Right? So remember, we had a lecture a while back about different ways to deal with these hard problems. Okay. Well, approximation algorithm is another method where basically here, instead of trying to find the optimal solution, we accept finding a approximately optimal solution. Okay, a solution which is almost as good as the optimal solution. And presumably, it's easier to find an approximately optimal solution than to find the optimal solution. Okay, so if you try to find the optimal solution, it's NP-hard, but if you just try to find a pretty good solution, it might be polynomial time solvable. Right? Yeah, so so to quantify this, we have this thing called the approximation factor. Okay, so this is just some, so if you take, let's say, a constant, or in some cases, we take alpha not to be a constant. Okay, we can take it to be a function of the problem size, for example. Okay, but here for simplicity, let's take alpha to be a constant. Then suppose you're talking about a maximization problem. Okay, so maybe in this problem, you're trying to get some sort of reward. So you want to get as much reward as possible. So in this case, if you have an alpha approximation algorithm, then that means that you get 1 divided by alpha times the optimal reward. Okay, so for example, if you get half of the maximum reward, then you have a 2 approximation algorithm, right? If you can guarantee that you get at least 1/3 of the maximum reward, then you have a 3 approximation algorithm. Okay, yeah. So our goal is to make alpha be as small as possible. Okay, in fact, if you have alpha equals 1, then that would mean that you get the optimal reward. Okay, but in many cases, it's NP-hard to get the optimal reward. So we allow alpha to be larger than 1. And the larger alpha is, the easier it is to find an approximation algorithm. Okay, so for example, if I have an algorithm which can get, if I have a 2 approximation algorithm, right, so I can get at least half of the reward, right, then automatically a 2 approximation algorithm is also automatically a 3 approximation algorithm, because if I can get half the maximum reward, then of course I can also get 1/3 of the maximum reward. Okay. So that means that the larger alpha is, the easier this problem becomes to solve. Okay. So if the problem is NP-hard for alpha equals 1, then if you make alpha larger and larger, then at some point this algorithm might become polynomial time solvable. But there are problems where even if you make alpha very large, the problem remains NP-hard. Okay, so we'll see some examples of that later. Yeah, but our goal is to make alpha as small as possible. Okay, so that's for maximization problems where you try to maximize your reward. And you can also consider minimization problems where maybe you try to minimize a cost for doing something. Okay, so in that case, you have an alpha approximation algorithm if the cost that you pay is at most alpha times the smallest cost. Okay, so that is the terminology we're going to use. And so now we're going to look at some approximation algorithms for different problems. So the first problem we're going to look at is called set covering. Okay, so the idea here is that suppose you have a set. Okay, so in this picture here, we have a set of all of these 12 dots. Okay, yeah, and then so in addition to these 12 elements, we're also given a collection of sets. Okay, so here you can see 6 sets over here. And what you want to do is to pick a subset out of these 6 sets, which can cover all of the dots. Okay, so for example, if you pick S3, S4, S5, right, then we can cover all 12 dots over here. Okay, all 12 elements. Okay. And you could have other, you can choose other sets also. Okay, you can choose, for example, let's say S1. Okay, you can choose something like S1, S5. You can choose this S4 over here, and then you can choose S6. Okay, so that's another way to cover all of the elements. Okay, so one application of this would be, or could be that, suppose these dots represented, suppose these elements represented classes that you're trying to teach. Okay, so let's say Shanghai Tech has 12 classes that it needs to teach. Okay, and then these sets represent teachers that you can hire. Okay, and so each teacher can teach a subset of these classes, right? So for example, this teacher S3 here, maybe he can teach these 4 classes over here. And so then what you're trying to do is you want to make sure that you can teach all of your classes. So therefore, you want to pick a subset. You want to pick some of these sets so that all of your classes get covered. Okay, so you're trying to cover all of your elements. Okay. However, you're trying to minimize the cost of these sets that you select. Okay, so each of these sets is going to have an associated cost. And this cost can represent like, the salary of the teacher. Okay, so your goal is to make sure you can teach all of the classes, but you want to hire the teachers and you want to minimize the total salary. Okay, so we want to find the cheapest way to cover all of these elements. So that's the set covering problem. Okay, okay, so just a bit more formally, let's say that, so let's define the problem this way. So we're given a collection F. We have a set of elements X, okay? And we also have a collection of sets, okay? So the collection is called F over here, okay? And each of the sets has a cost, okay? And we're guaranteed that if you take all of the sets, okay, then you can definitely cover all of the elements, okay? However, we don't want to take all the sets. We just want to take a subset of the sets. And our goal is to find a subset of these sets where the subset can also cover all of the elements. Okay. And furthermore, we want to minimize the total cost of all of the sets we select. Okay, so this is our problem. So for example, if all of the sets have the same cost, right, then if we take sets S3, S4, S5, that would be a minimum cost set cover of these elements. Okay. All right, any questions about this problem? Okay, so this problem is NP complete. Okay, so we're not going to try to look for an optimal solution to this. Instead, we'll try to find a solution which is approximately optimal. Okay. And in this case, we're going to see a log n approximation algorithm. Okay, so what I mean by that is, so if n here is the total number of elements, okay, then then you achieve a log n approximation. Okay, so for example, if n is let's say 10, and so this is natural log over here. Okay, so I'm not sure what the natural log of 10 is, but let's say it's something like 3. Okay. Then if you have 10 elements, you achieve a 3 approximation. Okay. Right now, if x is larger, if n is larger, if let's say you have 100 elements, okay, then you might get, then your approximation factor increases. Okay, so let's say log of 100 is something like 6. Okay, so if you have 100 elements, you only get a 6 approximation. Oh, and by the way, so if you get a 6 approximation, that means that the cost of these sets that we pick is going to be at most 6 times the minimum cost. Okay, yeah. So the more, so the more elements we have, the worse our approximation factor becomes. Okay. Right, now the algorithm for, so our approximation algorithm is going to be a greedy algorithm. Okay. So a very natural idea to use is that we want to pick sets which can cover the points in the cheapest way. So what I mean by that is, suppose you have a set which can, suppose you have a set which has a large cost. Okay, so then maybe a priori you don't want to use that set. But if this expensive set can also cover many, many elements, then it's worthwhile to use that set, right? Because you pay a high cost, but then you get a lot. You cover many, many elements. Okay. On the other hand, you might have a set which only covers a few elements. Okay. So that kind of looks like a bad set. But if that set is very, very cheap, then you also want to use that set, right? Because even though you don't get that much, right, you don't cover many elements, you also pay very little. Okay, so that's also a good set. Okay. Yeah, so basically we want to look at the amount of cost we pay for each element that we cover. Okay, so this is like a per unit cost. And we want to pick sets which have the very small per unit costs. Okay, so to make that a bit more formal, so for each set, suppose it's got a cost of C. Okay, so we pick a set and let's C be its cost. And let's let M be the number of points it covers. Okay, and so then the per unit cost for this set is going to be C divided by M. Okay, and now we want to choose the set with the smallest per unit cost. Okay, yeah, so that's the basic idea. Yeah, and then after you choose a set, okay, then since you're going to cover some points using the set, then you're going to remove all of the points it covers. Okay, and then we're going to look at the remaining points. Okay, so those have not been covered yet, and then we also have some remaining sets, and we're going to look for the per unit cost for the remaining sets, which can cover these uncovered points. Okay, so yeah, so for all of the sets that we can still select, we don't care if they can cover some of the already covered points. Right? We only care how cheaply they can cover these uncovered points. Okay, yeah, and so okay, so here's the algorithm. Okay, okay, so in this algorithm, F here is the entire set of sets. Okay, it's a collection of sets. Okay, and the union of all these sets is X. And then for each set in this F, right, we're going to write cost of S to be the cost of that set. Okay. All right, and then U here is going to be the set of elements that we have not covered yet. Okay, so initially when you start the algorithm, you haven't covered any elements. Okay, so then U is all of U is all of X. Okay, but as you run the algorithm, you cover more and more elements. So then U gets smaller. And then C here is the set of sets that you select. Okay, this is the collection of sets that you eventually output. Okay, so initially the uncovered elements are all of the elements, and then initially we haven't selected any set. Okay, all right, and then we're going to run a while loop, and then while there are still some elements that we have not covered. Okay, so while U is not equal to 0, then C is the sets that we've already selected, so we cannot select those anymore. Okay, so then instead we're going to choose some set out of this collection minus C. Okay, and we're going to choose S, which minimizes the per unit cost for covering these uncovered elements. Okay, so then here what we're doing is we're looking at the cost of the set S, right? And then we're looking at, okay, this S, how many uncovered elements can it cover? Okay, so yeah, right. So because we still have some elements U that we need to cover. Okay, so we only care how cheaply S can cover these uncovered elements. Okay, so that's why we do S intersect U. Okay, all right, and we're going to pick the S which minimizes this per unit cost for the uncovered elements. And then we're going to add that S to our set cover, right? And then also we're going to take all of the elements that S covers, we're going to take that out of the uncovered set. Okay? And then we just keep running this until we have covered everything, right? Until U equals 0, empty set. Okay. Yeah, so that's the greedy algorithm that we have. Any questions? Okay, right. So now let's show that this algorithm is correct. Yeah. Okay. So so first of all, we need to show that the answer it produces is actually a set cover. Okay. And then after that, we'll show that it achieves this log n approximation factor. Okay. So first of all, the reason that we actually output a set cover, okay, is simply because, well, this algorithm keeps running until we have no more uncovered elements, right? Until we have covered all the elements. Okay, so you keep choosing sets until you cover everything, and you know that if you choose all of the sets, it's possible to cover everything. Okay, so then eventually this algorithm is going to terminate, and when it terminates, we've covered all of the elements. So we output a set cover. Okay, so the next thing to do is to show that this algorithm achieves a natural log n approximation factor. Okay, and where this natural log n comes from is from this the sum of a harmonic series. Okay, so what we'll actually prove is that the approximation factor achieved by this algorithm is bounded by the sum of this harmonic series. Okay, which in turn is approximately equal to natural log of n. Okay, yeah, and again, this approximation factor means that if the actual minimum cost of a set cover is v, okay, then the cost that we have, right? So whatever we output, that's got a cost of at most log n times v. Okay. Yeah, and so so the basic idea for this proof is that we're going to bound the cost of the entire set cover by looking at how much our set cover on average uses for each element that it covers. Okay. Remember, the idea for the algorithm is to to choose the cheapest way to cover each element on average. Okay, and so we're gonna bound that cost. Okay, the average cost to cover each element. Okay. Okay. So the way we're going to do this is, yeah. So our cover is the set C. Okay. So we added the sets into C one by one. Okay. And so let's just order all of the sets in the order that we added them. Okay. So S1 is going to be the first set that we add, right? S2 is the second set, and so on. And let's say that in total you use M sets. Right, and then the cost of the cover that we output, okay, well, that's just equal to the sum of all of these sets that we have. Okay, so the sum goes from 1 to m. Oops. Oops. All right, sorry. What is this? Okay, I can't erase for some reason. Okay. Ooh, just. All right, so this, yeah, so the sum goes from 1 to m. Okay. All right. Okay, so in addition to ordering the sets this way, okay, we're also going to order the elements in this way. Okay, so we're gonna so we're gonna order the elements as like E1 up to En. Okay, where this ordering is determined by when these elements got covered. Okay, so for example, let's say that so we picked set S1 first, and let's say it covered elements E1, E2, E3. Okay, so then these three elements are the first three elements to get covered. Okay. All right, and then next, let's say you picked set S2, okay, and let's say that S2 covers let's say it covers let's say it also covers E3, okay, but it also covers E4, E5, okay, so then E4 and E5 are the next uncovered elements to get covered, okay, and then let's say you have you have an S3 over here, and let's say it covers E6, E7, right? Yeah. So anyways, so we're going to order all of the elements by the order that they covered, that they are covered. Okay. Now, one thing we know is that if you look at so our sets, we picked a total of m sets, right? So then if you look at all of the elements covered by the set, right, then we know that this is all of the elements in X, because all of these sets together, they form a set cover. So they cover all of the elements of X. Okay. So that means that if you take all these elements E1 up to En, right, then this is equal to the set X. Okay. All right. Now let's let Ni be the number of new elements that each set covers. Okay. So for example, so for example, N1, right? So S1 covers 3 new elements. Okay. So M1 is equal to 3. Okay. N2 is the number of new elements that S2 covers. Okay, so S2 covers 3 elements in total, but there are only 2 new ones. Okay, so therefore N2 is going to be 2. Okay, and then n3 is also going to be 2 because S3 here covers 2 new elements. Okay, yeah. Okay, so now what we're going to do is, remember the goal is to cover these new elements as cheaply as possible. Okay, so the way we're going to keep track of our cost is we're going to divide the cost of the set that we use. Okay, we're going to divide it evenly among all of the new elements it covers. Okay, so in other words, if E is a newly covered element by Si, okay, then we're going to say the cost of E is just the cost of this Si divided by Ni, okay, which is the number of new elements that Si covers. Okay, so then once we have that, then then we have this expression over here. So this sum is going to go from 1 to n, right? So now if you add up the costs of all the elements, okay, so for example, let's say that you have some Si which covers 3 elements, okay, then each of these elements gets 1/3 of the cost of S. Okay, so then if you add up all 3 elements, then you get exactly the cost of S. Okay. So in other words, if you go through all of the elements 1 up to n, okay, then the total cost that you pay for all of these elements is that, well, each of these Si's, so now here I is going to go from 1 to m, right? So each of these Si's is going to cover Ni new elements, okay? It's going to cover Ni new elements. And each of these newly covered elements has a cost of Si divided by Ni, okay? Yeah, and so that means that if you add up the costs of all the elements, then this is equal to this expression over here. Okay, but then this expression, right, the ni's just cancel, and so this expression ends up being equal to just the sum of the costs of all the sets we selected. Okay, which is the cost of our set cover. Okay, so in other words, what we're trying to say is that if you add up the costs of all the elements, where each element has a cost which is defined in this way, then if you add up all the per element costs, then you get the total cost of the set cover. Okay, all right, and so now in order to, so we're trying to prove a log and approximation factor. Okay, so to do that, what we're going to do is to say that each element has a pretty small cost. Okay, so the cost to cover the kth element, the cost of the kth element that we cover. Okay, so remember that we ordered all these elements by the order that they get covered. Okay, now the kth element, okay, so for example, this guy is k equals 5. Okay, what we're saying over here is that the kth element, the cost to covering him is going to be at most the optimal cost. Okay, the minimum cost set cover. We're going to say that this is opt. Okay, this is the cost of the minimum cost to cover all of the elements. Okay, yeah, so the cost for the kth element is going to be opt divided by n minus k plus 1 for any k. Okay, so what that means is if you look at the first element, okay, so then k equals 1 here. So then that bound was saying that the cost to covering the first element is at most opt divided by n. Okay, so that's a very small cost. Now the cost for the second element, right, k equals 2 here, then the cost is going to be at most opt divided by m minus 1. Okay, so that's a somewhat larger cost, right? So it's more expensive to cover E2 than to cover E1. Okay, and then for E3, right, the cost is going to be at most opt divided by n over 2, m minus 2. Sorry, m minus 2. Okay, so it's even more expensive to cover E3 than E2. Okay, so that means that every one of these elements gets to be more and more expensive to cover. Okay, and in fact, for the final element, right, for the so that one is n equals that one is k equals n. Okay, so for the final element, all we can say is that the cost we pay for the final element is at most opt. Okay, where opt here is the cost to cover all of the elements using the optimal cover. Okay. Yeah, so again, what we're saying is that the cost to covering these elements increases from opt over n, which is very small, but it keeps getting larger and larger. Okay, so it's more and more expensive to cover the later elements. Okay? At least that's what our proof can prove. Okay, that it might not actually happen in practice, but our proof, right? We can only provide this kind of bound on the cost. Okay, so now why do we want to prove this statement? Okay, why do we want to prove this statement over here? Okay, it's because if we have this statement, okay, then we know that the total cost of our cover is just equal to the sum of all of these per element costs, right? That's what we said over here. Okay, and then if we can prove this bound over here, right, then each of these the cost of ek is going to be at most opt divided by m minus k plus 1. Right? And so now you can just take the opt out from over here. And then now you see that you have the sum of a harmonic series in this sum. Right? Yeah, because you have like 1 over n and then plus 1 over m minus 1 plus 1 over m minus 2 and so on. Okay? Yeah, so then you have the sum of a harmonic series, which comes out to approximately log n. Okay? So therefore, in total, this sum here is going to be at about log n times the optimal cost, the minimum cost. Right? And so that means that our cost is going to be about log n times the minimum possible cost. Okay? So if we can prove, this statement over here, then we've proven our approximation factor. Okay. All right. So so now let's look at these per element costs. Okay. So now let's just pick any element, any arbitrary element ek. Okay. And suppose Sj is the set which covers ek for the first time. Okay. So for example, now let's go back to our picture, right? So if you pick E4, right, then S2 is the set which covers E4 for the first time. Right? If you pick E6, then S3 is the set which covers him for the first time. Okay. Right, so then what we're going to do is we're going to look at the sets, the elements after ek. Okay, so we're going to look at elements ek plus 1 all the way up to en. Okay, the elements which have not been covered yet. Okay. And now we're going to look at how the optimal cover actually covers these elements. Okay, so so these elements have not been covered yet. Okay, so we're going to call them U for uncovered. Okay. And let's look at how the optimal cover covers these elements in U. Okay. And so suppose the optimal cover is going to use R sets in total. Okay, so it's going to use sets C1 up to CR. Oh, by the way, I should mention that in the so I had a typo in the previous version of the notes. Okay, so I called this thing CM here. Okay, so I said there were like M sets, M of these C sets. Okay, so I don't want to use M because M here is supposed to denote the number of sets that we use, that our algorithm uses. Okay, so I want to use a different variable here, so I'm going to use R here for the number of sets that the optimal cover uses in order to cover just these currently uncovered elements. Okay, right. And now also and suppose each of these and suppose each Ci covers M prime I elements of U. Okay, so C1 is going to cover M prime 1 elements of U. Okay, C2 is going to cover M prime 2 elements of U, and so on. All right, so now we're gonna we have some like observations about these values. Okay, so the first thing is that if you add up all these m prime values, okay, so this is I guess going from 1 to r. Okay, yeah, right. So if we add up these m prime values over all of the sets that the optimal cover uses, then this is going to be at least m minus k plus 1. Okay, and the reason is that these sets C1 up to CR. These are the sets that the optimal cover uses in order to cover the set, right? And so if each Ci covers m prime I elements, right, then if you look at the total number of elements that these C sets cover, this has to be at least the size of the set. Okay, and the size of the set is just m minus k plus 1. Okay, that's why if you add up the size of all the C sets, you get at least n minus k plus 1. Okay, so that's the first observation. Okay. So the second observation is that if you add up the costs of all of these sets, okay, it's going to be at most opt. where opt is the cost of the minimum set cover. Okay. And this is just because these CI things, right? These CIs are a subset of the optimal cover, right? These CIs are only used to cover these U elements. Okay, but there are also other elements that we haven't even considered yet. Okay. So therefore, these C sets are a subset of the optimal cover, and the optimal cover itself has a cost of opt. And so therefore, the cost of the C sets is going to be at most opt. Okay. Okay. Now, another observation is that if you look at all of these sets which cover these uncovered elements, all of these C sets, right, then none of them are among the first J-1 sets that we selected. Okay, so remember what we're doing over here is that we're focusing on one, let me just clear this up a bit. Okay, we're focusing on one particular element, EK, right? And we're looking at the set which covers EK for the first time. Okay, and so what we're saying is that if you look at these C sets which cover these uncovered elements, okay, these C sets are not among the first J-1 S sets. Okay, so in other words, let's go back to the previous example we had. Suppose we are focusing on, suppose K here is going to be this element. Okay, so we're looking. So then S2 is the set which covers E4 for the first time. Okay, and now U is going to be all of these remaining elements which are still uncovered. Okay, and then we have a bunch of sets, a bunch of these C sets. Okay, and these are going to cover various elements from this U. Okay, and what we're saying is that S1 is not one of these C sets. Okay, yeah, so right, so this is like, let's say C1, C2, and so on. Okay, so we're saying that since S2 is the element which first covers, is the set which first covers E4. Okay. Then we are saying that S1 is not among any of these C sets. Okay, and the reason is that if S1 is one of these C sets, okay, well, these C sets, they all cover these elements from E4 up to En, right? So if for example, let's say C1 here, let's say it covers let's say C1 covers E4, E5, E6. Okay, and now if S1 was actually equal to C1. Okay, then that means that S1 itself would cover like E4, E5, E6. Okay, but we know that we have not covered E4, E5, E6 yet, right? Because we're looking at, because we ordered all of these elements by the order that they're covered, and we're looking at E4 right now, and so that means that everything after E4 has not been covered by S1, right? But if S1 is equal to the set C1 over here, right? And then C1 by definition covers some of these E4, E5, E6 elements, okay, right? It covers one of these elements after E4. Okay? Then if S1 is equal to C1, then S1 itself would cover something like E4, E5, E6, or whatever, okay? And that's a contradiction, okay? So that means that, so that means that S1 cannot be among none of these earlier sets. Okay, S1 up to Sj-1 can be among these C sets. Okay, any questions about that? This one's a little bit tricky. So does that observation make sense? Okay, let's see, what does this say? So EK is a notation where the elements are covered in order. Then why one CI in optimal C covers elements in C? Okay, yeah. They don't have to cover things continuously. I'm sorry. Yeah. So I just drew things that way because it's easier for me to draw. So yeah, that's a very good question. Okay. So in general, let's go back to that picture. Okay. Yeah, I didn't mean to draw things this way. Okay. So it could be that you have let's say C1. It covers things like it can cover anything, okay? It can cover something like E5, E7, and then E10 or something like that, okay? They do not have to be continuous, okay? I just drew things this way because it's easier for me to draw. Sorry about that. Okay, any other questions? Okay, yeah. All right, so going back to this third observation here, what we're saying is that all of these sets that the optimal cover uses to cover elements ek up to en, okay, none of these sets are among the first j-1 sets that our algorithm used. Okay. Yeah. So basically, what we're trying to do with this observation. Okay. So why are we talking about this? Okay. It's because now we're trying to look at what is the jth set that we used. Okay. What is Sj? Okay. And so because none of these C1 up to CR are among S1 up to Sj-1. Okay. Then in the end, what we show is that Sj can be chosen from one of these C1 up to CR sets. Okay, that's why we want this observation. Okay, we want to show that when you select Sj, you have the freedom to choose anything from C1 up to CR. Okay, because all of these sets have not been chosen yet. Right, we've already chosen S1 up to Sj-1, so we are not allowed to choose any of these sets anymore. Okay, but because none of these C sets are among the first j-1 sets we selected, then when we go select the jth set, we can actually go select from one of these C sets. Okay, and it's going to turn out that one of these C sets is actually very cheap. Okay, so that means that when we go select the jth set, we can select one of these cheap sets. And that shows that our cost is not too high. Okay, that's what we're going to do. Okay, so so in fact, this is the fourth observation here, which is saying that one of these sets, C1 up to CR, okay, at least one of these sets is pretty cheap. Okay, so how cheap? The cost of Ci divided by the number of elements from U that it covers, okay, is going to be at most opt divided by m minus k plus 1. Okay, that's what we're going to show. Okay. And the reason for this is that suppose for contradiction that all of the sets in C1 up to CR, okay, suppose they all are have average cost, right? So this is the average cost for that set. Right. Suppose our average cost is all larger than opt divided by m minus k plus 1. Okay. All right. Then what you have is that, well, we know that opt is at least as large as the sum of all of these Ci costs. Right. That was one of our previous observations. Which one was it? That's this observation 2 over here. Right. Okay. And then also the sum of all of these C costs, right? Well, then you can just write this as the number of elements of U that it covers, that the Ci covers, right, times the average cost per element. Okay, so you can write things this way. Okay, and now if you assume that all of these average costs are larger than opt divided by m minus k plus 1, okay, then you can just do the substitution over here, right? And then after that, you can pull things out. Okay, so then you're going to get that this sum is going to be at least opt divided by m minus k plus 1 times the sum of all of these m prime i's. Okay, and now our first observation was that if you add up all of these m prime i's, you get at least m minus k plus 1. Right, and that was because these sets C cover all of the remaining elements. Right, covers all the elements from ek up to en, and there are m minus k plus 1 such elements. Right, sorry. Yeah, sorry about that. Okay, so then that would show that, so this thing, of course, is equal to opt, right? So now we get a contradiction. Okay, we get that opt here is actually larger than itself. Okay, so yeah, so intuitively, right, if you have these sets C1 up to CR, and they all together cover these m minus k plus 1 elements, right? These elements in U. Okay, then one of these sets has to have average cost, which is no more than opt divided by m minus k plus u. Okay, so that's our observation. Observation 4. Okay, so now we're almost done. Okay, so now we can basically put things together, and we can say that. So now we're looking at the jth set that we're picking. Okay, and we can say that the cost of cost Sj divided by Nj, that is for all the newly covered elements for Sj, right? So Sj covers some new elements. Okay, right. So if you look at the cost for each of these new elements, right, which is equal to this thing over here, we can show that this is no more than opt divided by this m minus k plus 1. Okay. And the reason for this is that when you choose Sj, okay, the only sets that you're not allowed to choose are the sets that you've already chosen. Right? Any other set you're allowed to choose. Okay. And what we said by observation 3 was that all of these sets that the optimal cover uses, right, a C1 up to CR, okay, to cover these elements in U. Right? None of these are among the sets that we've already chosen. Okay, so that means that Sj, when we choose Sj, we're allowed to choose any of these sets. Okay, and furthermore, by the fourth observation, we know that one of these sets, okay, at least one of these sets is actually pretty cheap. Okay, the average cost to cover an uncovered element, right, is going to be op divided by n minus k plus 1. Okay, yeah, and so now, because we have a greedy algorithm, right, then the way that we chose Sj was that we chose Sj to have the minimum cost divided by newly covered elements, right? Yeah. So therefore, let's say that C1 here, okay, is actually the set which which achieves this property. Okay, I'm trying to write a 1 over here. Okay, right. Then we know that when you choose Sj, you can choose something which is, you're allowed to choose C1 when you choose Sj. Okay, and so that means that whatever Sj you choose can be no more expensive, right? The average cost for the Sj that you choose can be no more than the average cost for C1, right? And the average cost for C1 is going to be no more than this op divided by n minus k plus 1. Okay, yeah. So since you're allowed to choose any set, since Sj can, is allowed to be any of these sets from C1 up to CR, right? Then because we're choosing the cheapest Sj in terms of average cost, then the average cost you pay for Sj is going to be no more than the minimum average cost for these C sets, and that minimum cost is no more than this op divided by n minus k plus 1. Okay. Any questions about this part? Okay, all right. So then what we and then also we have that the average cost for this Sj in terms of like newly covered elements. Okay, this is simply equal to the cost of Ek, right? Because Ek is the next element that we have not covered yet. Okay, it's Ek is the element which is first covered by Sj. Okay, yeah. So then the cost for Ej is just equal to the cost of Sj divided by the number of uncovered elements that Sj covers. Yeah, so therefore you have that the cost of Ek is also no more than this op divided by n minus k plus 1. And that was what we wanted to prove. Okay, we wanted to prove that each of these, the kth element has a cost which is at most this quantity over here, because once we have that, then again, you just add up this harmonic series over here, and you get that our total cost is going to be no more than log times the optimal cost. Okay, so that's the proof. Any questions about this? Okay, so then next we're going to talk about another problem. Okay, we're going to look at an approximation algorithm for another problem. So this problem is going to be a vertex cover. Okay, so we've actually seen vertex cover before, but let me just remind you what the problem is. Okay, so we're given a graph, right? And suppose right now it's like an unweighted graph. Okay, so the edges and the nodes. Oh, sorry. There is a question. So let me do this question first. Why not use log k to replace log n? So n is the number of elements. Okay, yeah. So let me erase some of the stuff. There's too much stuff over here. Yeah. So n is the total number of elements that we have. Okay. So what we are saying is that the cost of the kth element, okay, for where k goes from 1 to n. Okay. The cost of the kth element is bounded by this expression. Okay. So therefore, if you add up this thing from 1 to n, right, then you get log n. Okay. Any other questions? Does that make sense? Yeah, okay. Any other questions about set cover? Okay, yeah, so if you have questions, then just please ask and I can go back to set cover, okay? All right, but first, so we're gonna talk about this vertex cover problem. Okay, so so this is gonna be an unweighted graph, right? So all the nodes and edges only have weight 1. And what we're trying to do is to select a subset of the vertices, okay? And for each and we're trying to use the vertices to cover all of the edges. Okay, so for example, if you select this vertex, right, then it's going to cover all of the edges that it touches. Okay, so if you select D, it's going to cover 4 edges. Okay. And we're trying to select a subset of the vertices so that all of the edges get covered. Okay, so for example, if you select this guy, you cover these edges, right, and then we still have 2 uncovered edges. So maybe you select this guy, and then you cover these 3 edges, these 2 additional edges. Okay, yeah, so that's the problem. Okay. And here, we assume that everything's unweighted, so we just want to pick the minimum set of vertices to cover all of the edges. Okay, so of course, if you pick all of the vertices, then you can cover all of the edges. Okay, but now we're trying to pick the minimum set of vertices, the smallest number of vertices to cover all of the edges. Okay, so so this vertex cover problem is NP complete. Okay. So previously we talked about this problem, and we said that, even though it's NP complete, you can have these algorithms which deal with like restricted cases of this problem. Okay, so for example, if you know the vertex cover is small, okay, if you know that you can cover the graph using, let's say, 10 nodes, okay, then we actually had a reasonably efficient algorithm to find a small cover of size 10. Okay. Or if you know that V has some special structure, like if V is a bipartite graph, right, then you can also develop some sort of algorithm to solve this problem. Okay. But now, this version that we're going to look at, we're not going to make any assumptions about V. Okay, so it's going to be a completely general version of vertex cover, in which case this problem is NP complete. Okay. All right, now, also, I just want to mention that vertex cover is actually a special case of set cover. Okay, and so what that means is that you can convert an instance of vertex cover to an instance of set cover. Okay, so so the way that you do this conversion is that if you're given this graph, right, then the element, and let's say you want to convert this vertex cover problem to set cover, then the elements in the set cover problem are now going to be the edges of this graph. Okay, because we're trying to cover all of the edges in vertex cover. So the elements in set cover correspond to the edges in the vertex cover. Okay, and then the sets correspond to these. The sets in set cover correspond to the vertices that we can pick in vertex cover. Okay, because remember that in vertex cover, each time you pick a vertex, right? So if you pick C, for example, okay, you can cover some of these edges, right? And the edges correspond to elements in set cover. Okay, so that's how you can map a instance of vertex cover to an instance of set cover. Yeah, so if you do that mapping, right, then you can just use the set cover algorithm to approximate vertex cover. But if you do that, you're only gonna get a log E approximation, where E is the number of edges. Okay. But instead, what we're gonna see is that we're gonna give a 2 approximation algorithm for vertex cover. Okay. And the reason we can give a 2 approximation algorithm is because vertex cover, when you map it to set cover, okay, then it's actually a very sorry, let me write this a bit nicer. Yeah, it's actually a very special instance. It's a very structured instance of set cover. Okay, so our previous set cover approximation algorithm can deal with any set cover problem, right, including unstructured instances. Okay. Whereas if you map vertex cover to set cover, it becomes a very special type of set cover. Okay, so for example, one special property when you map it over to set cover is that for each of these edges, right, so these are the elements that we're trying to cover, right, this can only be covered by 2 sets, okay, because this edge only has 2 endpoints, so you either have to use the set corresponding to B, or you have to use the set corresponding to A, right, so that's some sort of restricted types of sets that we're creating. Yeah. So anyways, because vertex cover is a special, very structured instance of set cover, then that means that we can actually get a better approximation algorithm. okay, because we don't have to deal with the full general case. Okay, right. So now let's look at the set cover the vertex cover algorithm. So it's so it's a very simple algorithm. Okay, so initially we are trying to cover all of the edges. Okay, and C is going to be the set of vertices that we select. So initially that's going to be empty. Okay, so then what we're going to do is, as long as we have more edges to cover, okay, then we're just going to take any edge which we have not covered yet. Okay, an edge UV that we have not covered yet. Okay, and then we're going to add both endpoints, both U and V, to our vertex cover. Okay, we're going to select both endpoints. And then after doing that, so once you select U, then you cover all of the edges adjacent to U. Right? And then once you select V, you also cover all of the edges adjacent to V. Okay? So therefore, after you add U and V to your vertex cover, you're going to remove all of the edges adjacent to either U or V, because you've already covered them now. Okay? You're going to remove them from D. Okay? And then you just keep doing this as long as you have some uncovered edges. Okay? And then in the end, you just output C as your vertex cover. Okay, so an example of this is, suppose you have this graph in A over here. Okay, then initially all of the edges are uncovered. So then in the first step, we just pick any arbitrary edge. Okay, so let's pick this edge BC. Okay, and then we're going to add both endpoints to our cover. Okay, and so once you add both endpoints to your vertex cover, then you're going to remove all of the edges which are adjacent to either B or C, because now they've been covered. Okay, so now we're going to remove all of these dotted edges. Okay, and now we have how many edges? We have 4 edges which are still uncovered. Okay, so then you're going to pick any uncovered edge. Let's say you pick EF. Okay, you're going to add both E and F to your vertex cover. You're going to remove all of the edges which are adjacent to either E or F. Okay, and so that leaves us with one uncovered edge, DG. Right, and then so we're going to pick that edge, add both endpoints, and then remove all of the adjacent edges. Okay, so in this case, there are no adjacent edges. All right, and in the end, the cover that we output is going to be, well, we selected BC, okay, and we selected EF, and we selected DG. So therefore, we output 6 nodes in our vertex cover. Okay, and it turns out that you can actually cover this graph using 3 nodes. Okay, you can cover it using these 3 blue nodes. And so you see that our vertex cover is twice as large as the smallest vertex cover. Okay, and we're going to prove that our cover is never more than twice as large as the smallest cover. Okay, so that gives us a 2 approximation algorithm. Okay, so the way to prove this is that, well, first of all, we have to prove that this algorithm outputs a vertex cover. Okay, and this is definitely true because we keep running this algorithm as long as we haven't covered all the edges. Okay, so yeah, so we keep running, and then so eventually we're going to cover all of the edges. Okay. Oh, right, and then each time you so each time in each iteration you add some nodes to your vertex cover, right, and then you remove some edges. Okay? But all of the edges that you take out, right, they have been covered by the nodes that you added. Right? Because if you look at this algorithm, right, so when you add nodes U and V, you're going to take out all the edges adjacent to either U or V because they're covered by U or V. So the only edges that you actually take out from the algorithm are edges that you actually covered. And then you keep running until you cover all of the edges. Okay, so therefore, eventually you get an edge, you cover all the edges. Okay, so next we're going to show that this algorithm achieves a 2 approximation. Okay, so that we only use at most 2 times as many nodes as the minimum cover. Okay, so to do this, let's let C star here be an optimal vertex cover, okay, which uses a minimum number of nodes. And also let's let A be the set of edges that our algorithm used, right? So, so for example here, right, we used 3 edges, these 3 red edges. Okay, so so now we're going to have some properties about A. So the first property is that none of the edges in A touch each other. Okay, so if we go back to this picture, you can see that none of these 3 red edges touch each other. Okay, and the reason simply is that for example, after you added the first red edge from B to C, right, then you took out all of the edges which touch B, which can touch this edge, right? Because you took out all of the edges adjacent to B and all the edges adjacent to C. And those are the only edges which touch BC. Okay? And so the next time that you picked an edge, when you pick EF, right, it's not possible to pick an edge which touches BC. Right? And then after you pick EF, you take out all the adjacent edges. So when you so the next time when you pick DG, right, it's not possible to touch EF or to touch BC. Okay? Yeah, so therefore all of the edges that we pick do not touch each other. Okay? Because each time you pick an edge, you remove all of the adjacent edges. Okay. Now the second fact is that each vertex in the optimal vertex cover, okay, it can cover at most one edge in A, right? A is the set of edges we pick. Okay. And the reason is that, if you pick some vertex in the optimal cover, okay, then this vertex, then all of the edges that's, so let's say that you picked some vertex V in the optimal cover, okay, then all of the edges covered by this V here, right, they all touch each other. Okay, so for example, if you pick this node V, okay, then which edges does it cover? Let's say it covers these edges. Okay, well, all these edges touch each other. Okay, but we know that none of the edges in A touch each other. Okay, so that means that if you pick this element element V over here, right, you can cover at most one edge from A, right, because all the edges that you cover touch each other, and none of the edges in A touch each other. Okay, and so that means that since each vertex in C star can cover at most one edge in A, okay, then, oh, right, and we also know that every edge in A has to be covered by some vertex in C star, right, because C star is a vertex cover, so it has to cover all of the edges, including all the edges in A. Okay, so that allows us to conclude that the size of C star has to be at least the size of A. Okay? Because C star has to cover all of the edges in A, and each element in C star can cover at most one edge in A. So therefore, the number of elements in C star has to be at least the size number of edges in A. Okay, and now what about our algorithm? Okay, well, our algorithm, the size of the vertex cover that we output is just 2 times A. Okay, because each time we pick an edge, we pick both endpoints. Okay, so if you pick 10 edges, you're going to pick 20 points. Okay. Right, yeah, so our vertex cover has size 2 times A, and the minimum cover has size at least A. Okay, so that means that the number of elements, the vertices that we use, divided by the number of elements that the optimum uses, right, is going to be at most, this thing over here, right, and this is going to be at most 2. Okay, so this means that our algorithm uses at most 2 times as many nodes as the optimum. Okay, any questions about this? Okay, right, so next we are going to, let me switch over to this thing over here. Okay, so next we're going to talk about an extension of vertex cover into the weighted case. Okay, so the previous, in the previous case, none of the, it was completely unweighted, right? So, so the vertices did not have any weights on them, okay? So now we're going to consider a more general version of vertex cover where the vertices now have weights. Okay, and our goal is still to cover all of the edges. Okay, but now because all of the vertices have weights, then we want to pick a subset of the vertices with minimum total weight, which can cover all of the edges. Okay, so for example, if you pick these 4 blue vertices over here, then they're going to cover all of the edges, and their total weight is going to be minimum among all possible ways to cover all the edges. Okay, so this is going to be a weighted vertex cover. And because we now have weights, then our previous algorithm doesn't work anymore. Okay, because our previous algorithm only counted the number of vertices that you used. It didn't consider the weights of any of the vertices. Okay, so that previous algorithm is not going to give you a two approximation anymore. So we're going to develop a new algorithm. And this new algorithm is going to be based on something called integer linear programming. Okay. So integer linear programming is an extension of linear programming, which we talked about last time. Okay, so remember that linear programming, you have a bunch of, so you have a linear objective function subject to a bunch of linear constraints. Okay. And integer linear programming is basically the same thing, except for in addition to these linear constraints, you also have something called integrality constraints, meaning that all of the values for the variables in this integer linear programming need to be integers. Okay, in linear programming, you don't require the variables to have integer values. Okay, they can take any real values. Okay, any non-negative real values is okay for linear programming. Okay, but for integer linear programming, you require that all of the variables have integer values. Okay, and now you can actually model the weighted vertex cover problem using integer linear programming. Okay, so the way that we're going to do that is that if you have a graph with, let's say, n vertices, okay, then we're going to create one variable. So we're going to create an instance of integer linear programming. And we're going to make one variable for each vertex. Okay, so if you have n vertices, we're going to make n variables. Okay, and these variables have to have integer weights, which are either 0 or 1. Okay, so because we're dealing with integer linear programming, we can restrict the variables to have integer values, and furthermore, we can restrict them to have values within some range. Okay, so in this case, we're going to restrict all the variables to either be 0 or 1. Okay, and now the way that you interpret this is that if xi is 0, right? So xi corresponds to a vertex I. And xi equals 0 means that you do not select vertex I into your vertex cover. Right? You don't put vertex I into your vertex cover. Okay? And then xi is 1. If xi is 1, then you do put vertex I into your vertex cover. Okay? So that way, these xi's exactly describe a vertex cover. Right? A vertex cover is just exactly the set of xi's which are equal to 1. Okay? Right, and so so what is our objective in this formulation? Well, our objective is to I claim the objective is this. Okay, it's the sum of all of these wi's times the xi, where wi is the weight of vertex I. Okay, and the reason this is the correct objective is because since each of these xi's is either 0 or 1. Okay, then if you have xi is 0, then that means that xi is not in the vertex cover. And so we don't need to pay for node I. Okay, so then this term disappears. Okay, and on the other hand, if xi is equal to 1, right? Oops, sorry. If xi is equal to 1, then we are going to put xi into the vertex cover, and in that case, we have to pay for the cost of this vertex I, which is wi. Okay, so then if you sum up this wi times xi over all of the vertices, right? Then that's exactly the cost that you pay for the vertex cover. Okay, yeah, so this is the objective that we are, and we're trying to minimize the total cost. Okay, and then lastly, we need to have this constraint that we actually achieve a vertex cover. Okay, meaning that we cover all of the edges. Okay, so how do you guarantee that you cover all of the edges? Well, I claim that this constraint here guarantees that we cover all of the edges. Okay, so this is saying that for each edge ij, okay, if you look at the variables xi and xj, right, and you add them up, this has to be at least 1. Okay. And the reason this guarantees that we cover this edge is because in order for xi plus xj to be at least 1, then since each of these is either 0 or 1, okay, then we need at least one of xi or xj to be 1. Right? We cannot have both xi and xj be 0 and still satisfy this constraint. Okay? But if either xi or xj is 1, right, then that means that either we pick xi or we pick xj, right, or we pick both of them. And in all of these cases, we cover this edge ij here. Okay, so as long as you can satisfy xi plus xj is at least 1, then you're going to cover this edge ij. Okay, and then we're going to impose this constraint for every edge in the graph. Okay, and so that's going to guarantee that we cover all of the edges in the graph. Okay, any questions about this formulation? Okay, right, yeah. So then here's the entire integer linear program written out, right? So we're trying to minimize this cost over here, which is just equal to the cost of our vertex cover, right? So then if we impose this constraint for every single edge, then we guarantee that every edge gets covered, right? And then also we have this integrality constraint over here where we want to say either we, if xi is 0, then we don't use that node, and if xi is 1, then we do use that node. Yeah, and so this means that if we can somehow solve this integer linear program optimally, okay, so if x star is a optimal solution to the ILP, right, then if you just pick all of the xi's which are equal to 1, then this is also equal to a minimum weight vertex cover. Because this ILP exactly models the weighted vertex cover problem. Okay, so the optimal solution to the ILP is also the optimal solution to the vertex cover. Okay, right. Yeah, and then also you can write this a bit more nice. Yeah, so this particular ILP, right? So this is a instance of the more general integer linear programming problem, where here you just have some sort of linear objective, right? And then you have a bunch of these constraints. These are also linear constraints, okay, right? And then finally you have these integrality constraints. Okay, so this is like the general formulation for ILP. And furthermore, you can write this general formulation a bit more compactly in matrix notation. Okay, so then this C, for example, is just the vector of all of these C values over here, these individual C values. Okay, and this A here is going to capture all of these different constraints over here. Okay, yeah. So, anyways, I just want to show you that you can formulate all of this very compactly. Okay, yeah. Okay, so then what we see is that if you can solve this particular ILP optimally, okay, then you can solve a vertex cover optimally. And we know that vertex cover is NP complete. Okay? And so that means that solving this ILP, right, this particular ILP, solving this thing is also NP complete because it's equivalent to solving vertex cover. Okay? And that also means that in general, solving general ILPs, okay, so is NP complete, right? Even solving this one particular ILP is NP complete. So solving general ILPs is also NP complete. Okay, so therefore, it seems like we haven't gotten anything by changing our problem to integer linear programming, right? Because integer linear programming is still NP complete. Okay. However, we actually do get something by converting vertex cover to integer linear programming, which is that now we can convert integer linear programming to regular linear programming. Okay, so regular linear programming, or just simply linear programming, okay, the main difference, or basically the only difference, is that we do not have this integrality constraint anymore in linear programming. Okay. So as soon as you take out this integrality constraint, okay, then the problem changes from being NP complete to polynomial time solvable. Okay? Because if you have this integrality constraint, right, then we know this problem is NP hard. Okay? But if you take out the integrality constraint, then you just have linear programming, and we know that there are polynomial time algorithms for linear programming. Okay? So what we're going to do is to convert vertex cover to integer linear programming, and then convert integer linear programming to regular linear programming. Okay. All right, and so we have several observations. The first observation is that if you solve this linear program, okay, then the optimal solution for the linear program is no more than the optimal solution for the integer linear program. And the reason is simply that the linear program has fewer constraints than the integer linear program. Okay, so if you're trying to minimize a function and you have fewer constraints, then you can possibly get a smaller value as your optimum. Okay, right? So LP and ILP are exactly the same, except for LP doesn't have these integrality constraints. Okay, so therefore, the optimal value for LP may be less than the optimal value for ILP. Okay, right. Now, the problem with LP, okay, so we converted vertex cover to ILP to LP. Okay, but the problem is that if you solve this LP, okay, the solution you get may not correspond to a vertex cover. Okay, because for example, let's say that you solve this you solve this LP, right? And let's say that you get this as your solution. Okay, so all of these variables, right? So let's say this x1 here is 1/2, right? x2 here is 1/2, x3 is 1/2. Okay, right? Then how do you convert these x values to a solution for vertex cover? Okay. In ILP, it was easy to convert an ILP solution to a vertex cover, right? Because you just take whatever variables were 1, then you put that into your vertex cover. That's exactly your solution. Okay. But in linear programming, because you don't have the integrality constraints, you could end up with x values which are not 0 or 1, right? They can be fractional, right? And then what do you do with these fractional values, right? How does this tell you what your vertex cover should be? Okay. Well, the approach we're going to use is something called rounding. Okay, so this is a general approach that's used in these situations. Okay, so what we're doing, so this thing is called LP relaxation. So LP relaxation is to take an integer linear program, okay, and just remove the integrality constraint in order to get a linear program. And this process is called relaxation. Okay, because you take away some of the constraints, so you relax the constraints you have to satisfy. Okay, and then we're going to solve this relaxed problem, but now we might end up with a non-integer solution. Okay, and the final thing we're going to do is to take this non-integer solution and round it in some way to obtain an integer solution. Okay, and then that integer solution will correspond to a solution to vertex cover. Okay, so we need to take the possibly non-integer solution returned by the LP and convert it to an integer solution. Okay, and to do that, so suppose you have suppose x star is the optimal solution returned by the LP. Okay, then we're going to look at all of the x values in this x star which are at least 1/2. Okay. And then we're going to add all of these, so each of these xi's corresponds to a vertex. Okay, and we're going to add all of those vertices into our vertex cover. Okay, so our algorithm, once again, is we start with this ILP, right? We convert it to an LP by taking out these conditions. Okay, we solve this LP in polynomial time. Okay. And then finally, we look at all of the solution values, which are at least 1/2, and then we add that to our vertex cover. Okay, so that's the algorithm. And the claim is that when you do this, you achieve a vertex cover, and the cost is at most 2 times the minimum cost, 2 times the optimum cost. All right, so we're going to prove this. So the first part is to prove that when you choose this S, you actually achieve a vertex cover. Okay, and the reason is because, so let's pick any edge E. Okay, we want to show that our solution covers edge E. Okay, and the reason is because, our solution satisfies all these constraints. Okay, so in particular, for this edge ij, right, we have that xi plus xj, is at least 1. And so that would mean that xi or xj, xi star or xj star has to be at least 1/2, right? Or both. Okay, because if both of these are less than 1/2, then you cannot satisfy this constraint. Okay, and so if either xi or xi star or xj star is larger than 1/2, then whenever it's larger than whenever it's at least 1/2, we're going to include it into our vertex cover. Okay? So that means that we include at least node I or node j, at least one of these. Okay? And that would mean that this edge ij gets covered. Okay? Right. The next property we're going to show is that, okay, so that shows that we output a vertex cover. Okay. The next thing we're going to show is that this vertex cover is at most 2 times the optimal vertex cover. Okay. And this is because if you, so now let's let S star here be an optimal vertex cover. Okay. And so what we know is that because we did this LP relaxation, right, then if you add up the costs of all of these WIs in the optimal vertex cover, right? So you can also write this as a WI times XI, right? Because in the optimal cover, these XIs are either 0 or 1. Okay, so if it's 0, right, then we don't count it, and if it's 1, then 1 times WI is just WI. Okay, right? Yeah. So then this optimal cover, right? We know that this is at least as large as the minimum LP solution. Okay, because this is the ILP solution, right? The optimal ILP solution. And this one is no more than the optimal LP solution, right? The LP solution is actually to add up over all of the vertices, okay? But we don't even do that. We just add up over a subset of the vertices. Okay, so the LP solution is going to be at least as large as this quantity, right? And this thing over here is going to be at least as large as the optimum LP solution. Okay, so therefore, this optimal vertex cover is going to be at least as large as this quantity over here. Okay, all right, and now this quantity, okay, this set S, right? This only we only include an element xi in S if xi's value is at least 1/2. Okay, so that means that for all the elements in S, right, all their xi values are at least 1/2. Okay, and so that means that we can pull out the 1/2 over here, right? So we get a 1/2 over here. Okay, and then what we have left over here, right? This is just the cost that our algorithm pays, right? Because we're adding up over all of the elements that we selected, all the nodes that we selected, and we add up their weights. So this is just our cost, our algorithm's cost. Okay, and then this thing over here is the optimum cost. So this is saying that the optimum cost is going to be at least half of our cost. Okay, in other words, our cost is no more than twice the optimum cost. Okay, yeah, so that shows that our so that shows that we achieve a 2 approximation. Okay, any questions about this? Okay, so just a few more things I want to mention about this vertex cover problem. Okay, so we achieved a 2 approximation, right? And it turns out that if we assume P is not equal to MP, okay, then you can prove that you actually cannot approximate this problem very well. Okay, not only can you not solve weighted vertex cover optimally, you can't even approximate it that well. Okay, so it's not possible to. So we have a 2 approximation factor. Right, and we want to make this as low as possible. Okay, but it turns out that you cannot make this approximation factor lower than 1.36 if P is not equal to MP. Okay, yeah, so it's not possible to find like a a 1.01 approximation. Okay, that's not possible. Right, this approximation would mean that your solution is only 1% larger than the smallest. Okay, but this result shows that you can't do that. Okay, if P is not equal to MP. Okay. However, even if this, even though we have this result, it might be possible to find like a 1.5 approximation. Okay, a 1.5 approximation is better than what we have now, right? And it doesn't contradict this lower bound. Okay, and so it's like an open question whether it's possible to find an approximation which is better than 1.36, which is slightly larger than 1.36. Okay, so this is like an open problem right now. But many people suspect that it's not possible to find such an algorithm. Okay, it's not possible to find, for example, a 1.5 approximation. Okay, and this is because there's another conjecture. Okay, so this is called the unique games conjecture. So just like, P not equals to NP is a conjecture because we can't prove it, right? This unique games conjecture is another conjecture, but it's also very reasonable, and most people believe that this conjecture is true. Okay? So assuming this unique games conjecture is true, right, then it's not possible to find a better than 2 minus epsilon approximation. Okay, so currently we have a 2 approximation. Okay, and what this result is saying is that even if you want to look for a slightly better approximation, like a 1.99 approximation, okay, this is not possible if the unique games conjecture is true. Okay, yeah, so that basically means that this 2 approximation that we have right now, right, is the best possible. But again, people don't know whether this unique games conjecture is true. So yeah, so it's like so a lot of people are interested in this conjecture because if this conjecture is true, it actually implies that many approximation algorithms that we have right now are optimal and cannot be improved. Okay, but we don't know whether it's true or not. So yeah, so to find out what this thing is, you can just go look online for what this is. Okay, so I don't have time to actually talk about this in detail. Okay, any questions about anything? Okay, so then we're going to continue our lecture next week, our lectures next week. And I think next week we're going to be back to the normal time. Okay, so our standard class time is from like 10:15 to 11:55. Okay, so I believe that next week we're going back to the standard time. Okay, yeah, so make sure that you join a bit later. Okay, all right, so then I will talk to you guys next week.